Dear students, today we shall be discussing about diffraction due to two slits. This will be largely based on your previous knowledge, whatever you have learned in the diffraction pattern of single slit, right? Now suppose we have two slits in this way, and since it is a Fraunhofer diffraction, we are placing a convex lens here, right? There is a single source of light that is illuminating these two slits. Suppose the width of each slit is E, and the distance between them is D, right? Now, for any ray of light or a wave that starts from the center, it goes through the lens and bends like this. Similarly, it passes through the lens, bends like this, and meets the screen. So this is the point of constructive interference or central maxima. Now, what about a ray of light that bends from the same point? It goes like this, bends like this. Similarly, a ray of light, it goes like this and bends like this. So you have another point. Say P2 and this was P1, the central maxima, right? Now, since this is the central position, the center of the slit, so the distance from this to this is E by 2. Similarly, the distance from this to this is E by 2. So what is the total distance between this and this point? Obviously, it is E by 2 plus D plus E by 2. And what is that? That is E plus D, right? Now we need to find the path difference between these two rays, this ray and this ray. And how do we do that? By drawing a perpendicular as always. This angle is theta. We are interested in this distance, path difference. Suppose this point is P, suppose this is B and this is C, right? So from the triangle we can find that sine theta is equal to BC by E plus D. This is the hypotenuse and its length is E plus D. E plus D. So this BC is equal to E plus D sine theta. So this is the path difference. Now we know that the consequent phase difference phi is given by 2 pi by lambda times the path difference. You know it, you have already done this many times. So the phase difference will be 2 pi by lambda, and what is the path difference? It is E plus D sine theta. We can also write it as phi is equal to 2 beta, wherein we have put the factor of beta equal to pi by lambda E plus D sine theta. Now we know that the intensity pattern on the screen is because of two slits at this time, slit 1 and slit 2. So what is the amplitude due to slit 1? We have already found that in the previous video, that R is equal to A naught sine alpha by alpha, and you are aware with what is alpha and what is A, right? Similarly, R2 due to second slit will be again A naught sine alpha by alpha. And why are they same? Because the two slits are being illuminated by a common source of light. So these resultant amplitudes will be same. Now the total intensity. Now we can make from here, I'm going here. Now if you recall the Young's double slit experiment, how do we find the resultant intensity or the resultant amplitude? The resultant amplitude is R1 square plus R2 square plus 2 R1 R2 cos phi, where phi is the phase difference between these two, right? Now what is that? So this is A naught sine alpha by alpha square plus again A naught square sine square alpha by alpha square plus this factor 2 times this A naught square sine square alpha by alpha square and cos phi, all under root, right? So from here we can take it to next page, that is the resultant intensity R is equal to, of course this a naught square sine square alpha by alpha square is twice, plus twice a naught square sine square alpha by alpha square cos phi, right? Now we can take this factor common, a naught square sine square, so it comes out as a naught sine alpha by alpha, right? And inside we are left with how much? We are left with twice 1 plus cos of phi, right? Now we know this formula that 1 plus cos theta is equal to twice cos square theta by 2, or 1 plus cos of 2 theta is equal to twice cos square theta. Now we will make use of the same here. So this will be a naught sine alpha by alpha under root 2. For this we can substitute this, that it is twice cos square phi by 2. 2 into 2 is 4, that will come out as 2. So this is 2a naught sine alpha by alpha, and this will be cos of phi by 2, right? And if you go to the previous calculations, what is this phi by 2? Phi by 2 is actually beta from this. So you can substitute that this is 2a naught sine alpha by alpha cos beta. So this is the resultant amplitude due to the two slits. And now what is the resultant intensity? Obviously that is the square of amplitude, that is r square. So that is 4a naught square sine square alpha by alpha square cos square beta. If you recall, this factor gives the intensity distribution because of a single slit. Okay, now that is acted upon together with this factor cos square beta. So let us try to understand it first graphically. And how do we do that? It is, for instance, this is the intensity pattern due to a single slit, right? And then you will have this cos factor. We know that cos, the graph will be like this for cos square beta. And once these two disturbances act together, what do you think should be the resultant like? See, if you have a diffraction pattern like this and a cos wave like this, right? Wherever the crust falls on trough, it will eliminate, okay? So we will be left with zero intensity. So the resultant would be like this. This is the final diffraction pattern, right? But inside you will have some more patterns. Inside you will have some more patterns, right? At these places, actually, a crust has already fallen on this trough, and the resultant intensity is 0, 0. So when you look at the screen, you get the central maximum, but that is interspersed by minimas. Similarly, you get the first secondary maxima, but that is interspersed by dark bands. Similarly, on the right side, on the upper side of the screen, you get another maxima, but that is interspersed by the dark band. So this will be the intensity pattern on the screen. Now, let us find the conditions of maxima and minima analytically. So how do we do that? We know that we are involved with a factor of cos, right? So, but more appropriately, it is a cos square factor. So it is a cos square beta factor, right? We know that cos beta will be maximum when beta is equal to m pi. See, the values of cos of an angle range from plus minus 1. Basically, we say that the maximum value is plus 1 and the minimum value is minus 1. But because a square term is involved here, we will be taking both the values plus 1 and minus 1 into account, because square will turn both of them into positive, right? So we say that cos beta will be maximum and beta is equal to m pi. Now what is this beta? You have already found it. You have found that beta, and what is that? That beta is pi by lambda e plus d sine theta. So that is pi by lambda e plus d sine theta, and this is equal to m pi. Now pi and pi will cancel and you are left with e plus d sine theta is equal to m lambda, right? And what is this e plus d sine theta? It is the path difference. It is the path difference, e plus d sine theta. So whenever the path difference is an integral multiple of lambda, it will give us maxima, that is constructive interference or bright fringes. Now let us see when cos beta is minimum. That is, it is equal to 0. We know that cos is 0 when the angle is an odd integral multiple of pi by 2. Cos 90 is 0 and all odd multiples of 90, that is 0, right? So let us equate that. So beta is equal to this much. Again we'll put the value of beta, that is pi by lambda e plus d sine theta is equal to 2n plus 1 pi by 2. So pi and pi will go. We are left with e plus d sine theta is equal to, let's write it as m because we have used m in the upper expression. We shall continue with the same notation. M or n, it doesn't matter. So 2m plus 1, and this is lambda will go here. It is lambda by 2. So what is this? This is path difference. So whenever the path difference is an odd integral multiple of lambda by 2, the interference is destructive, corresponding to which we are going to get dark spots or dark fringes, right? Now if you recall this expression, these results are much like those of Young's double slit experiment, right? There also this was the condition for maxima and this was the condition for minima. Now what are the essential differences? In case of Young's double slit experiment, the distance between the two slits is narrow, it is small. So I shall write it on a separate page, that in case of Young's double slit experiment, the distance between two slits is small, right? Moreover, the width of the slit is also small there, but here it is a bit broader than that. So here you have an interference pattern because of this. So I hope that gives a complete description of diffraction due to two slits. But this will be largely based on your previous information, whatever you have learned in detail in the diffraction due to a single slit, because we have used those expressions directly here. So that's all about it.